All right, we're in section 3.1, starting chapter 3 today. And in chapter 3, what we're going to be doing is looking at applications of the derivative. We're not moving on to the next big calculus topic, which is integrals, until chapter 4. We're still dealing with the derivative, but kind of looking at some implications of the derivative of a function, information that we can glean from it and stuff like that. So to start with, we've already discussed in chapter 2 how there is this relationship between the derivative of a graph at some particular value and whether the graph is increasing or decreasing there. Or neither. You'll notice I put that in parentheses. So here's sort of a summary of that. Suppose the function f is differentiable on some interval. So again, remember that means that the derivative exists on that interval. If the derivative, so f prime of x, is positive, greater than 0 on that interval, then f is increasing on that interval. And the flip side of that, if f prime of x is negative on an interval, then f is decreasing on that interval. If the derivative of f is 0, then it's neither increasing nor decreasing. The graph would have a horizontal tangent at any point where that occurs. So here is a graph that sort of illustrates that. You have a parabola, and you can see on this interval from basically negative infinity, even though we can't see that far, negative infinity up to 2, our graph is going downhill. So it's increasing. And if you were to look at tangent lines to points on this curve all along that branch of it, they would all be going downhill as well. So they would have negative slopes. So again, the slope of those tangent lines is what our derivative represents. So we have negative derivatives corresponding to a decreasing function. Increasing over on this side is going to indicate that the derivative of our function f is positive. And then you notice I put a little blue horizontal tangent line right here at this vertex of this parabola, where our function is neither increasing nor decreasing at that exact point, but it's got a horizontal tangent, which means its slope is 0. So f prime would equal 0 there. Now, something important happens here too, and this is why I wanted to use this graphic to illustrate it. Being a parabola, this function has a lowest point, or at least the part of the graph that we can see has a lowest point. And the y-coordinate of that lowest point is what we call a minimum. So this graph has a minimum value of 1, because that's the y-coordinate of that point, but it occurs at x equals 2. So you'll notice throughout this section we talk about maximum and minimum values throughout the chapter, really. And we'll talk about what the maximum value is and where it occurs. What it is the y-coordinate of that point, and where it occurs is the x-coordinate of that point. So that lowest point, that minimum, is 1, and it occurs at 2. But a little bit more importantly, as we go from left to right, we have a decreasing trend in our function to that minimum, and then it increases away from it. So one way of identifying a minimum value is if our function decreases to a point where the derivative eventually becomes 0 and then increases away from it, we'll have a minimum value there. But another way of thinking of that is if our derivative goes from being negative to 0 to positive. We're going to use that to identify minimum values. And kind of the first step in a process like that is first finding where exactly that minimum value occurs by finding where my derivative was equal to 0, where that horizontal tangent occurred. Now, it's important to note that if a function does have a value where the derivative is equal to 0, that could be a place where we have a minimum value like this. It could also be a place where we have a maximum value, or it's possible that neither would occur. And here's an example where neither would occur. So this is a graph of a function that has a horizontal tangent right here at -1. And even though it's got a horizontal tangent, that point is neither a minimum nor a maximum, because for values on the graph that are near it, I have some that are smaller and some that are larger. Y-coordinates specifically are smaller over here, larger over here. So the horizontal tangent did not imply that there was a minimum or maximum value here, even though we ended up with one over here. Okay, that's going to be an important point. So There's other ways where we can end up with maximum and minimum values as well. What we're seeing on this page, let me just summarize this real quick, is where our derivative is equal to 0, where we get these horizontal tangent lines. Those are places where a maximum or minimum value could occur. So they have the potential to give us maximum or minimum values. Another way that a maximum or minimum value could occur is where a function fails to be differentiable. So one thing that we mentioned back in chapter 2 is that if you look at the graph of a function, if you have any corners or cusps, which we have both of those here, those are places where the derivative of that function does not exist. Even though the function does exist at those values, the derivative would not. So we say that the function f of x is not differentiable here or here. And what that tells me is that, well, what that ended up being happening here was that our function, even though it was not differentiable at either of these places, we ended up with a maximum value at one and a minimum value at the other. So places where a function fails to be differentiable are also places where maximum and minimum values could occur, but they don't necessarily have to occur there. For example, here, this function is not differentiable at x equals 4 because I have this vertical asymptote here. So clearly there's no maximum or minimum value at 4 because the function's not even defined there. But even as I get like arbitrarily close to 4, we get larger and larger values that never seem to like taper off anywhere. So putting all of this information together, if we're looking at a function and if our goal is to try and find maximum and minimum values for that function, it turns out that those will always occur in one of two places. They'll either occur where the derivative of our function is equal to 0, or where the derivative does not exist at all. In other words, where the function is not differentiable. Now, if that's the case, f prime of, if we are going to have a place where the function fails to be differentiable, but we have a maximum or minimum value, it's necessary that the function itself be defined there, even though the derivative does not necessarily exist there. Because there has to be a point on the original graph of f of x for that to be a maximum or minimum value. So putting all of that together, we have these things that are called partition numbers. And they come straight from this idea that we're after right now. Partition numbers of f prime, so the derivative of your function, are the x values where either one of these two things occur, where either f prime of x is equal to 0, or where f prime of x does not exist, okay? What these partition numbers do is they break up the number line, more specifically the x-axis, and the spaces in between those partition numbers, which are just intervals. We will either have our function will either be increasing or decreasing throughout that entire interval. So looking here, this graph had two places where the function failed to be differentiable. I don't see anywhere where I would assume a horizontal tangent is. So those are the two partition numbers, x equals 3 and x equals 5. That's where those both occur. On the interval from negative infinity all the way up to 3, it looks like the function is increasing that whole time. And then on the interval from 3 to 5, it's decreasing. And then from 5 to infinity, it goes back to increasing again. So the job of these partition numbers is to break up the number line or the x-axis into intervals on which the graphic is either only increasing or decreasing. And that's kind of the first thing that we want to be able to do, is determine the intervals on which a given function is either increasing or decreasing using this thing here, which we call the increasing decreasing test. So it's kind of a three-step process. First thing we do is we determine the domain of f. A function cannot be increasing or decreasing on intervals for which it's not even defined. So we should know first what is the domain of f so that we can then kind of know roughly where we're looking for these intervals of increase or decrease. Then, second step, we find the partition numbers of f prime. That's what we defined up here. So again, anywhere where the derivative either equals 0 or does not exist. And then 3, notice is a big step here. We do this thing called creating a sign chart of f prime by using those partition numbers to divide the number line into a bunch of intervals or subintervals. And then we use test points within those intervals to determine if the function is increasing or decreasing. Rather than read through all of this, I'm going to make this a little bit more clear with some examples. Okay, so let's start with this one. We have this function, y equals x cubed minus 27x plus 4, and our job is to determine where this function is increasing or decreasing. So the first step would be to find the domain of this function. And the domain of this function is all real numbers. The domain is the interval from negative infinity to infinity. That's another way of just notating the set of all real numbers. The second step is to find the partition numbers of this thing. So in order to find the partition numbers, I need to first find the derivative. That's going to be y prime. And the derivative is easy to find. That gives me 3x squared minus 27. Okay? And I want to find anywhere where this derivative either equals 0 or fails to exist. Now, I'm just going to say, going through the problems that you're going to be doing in the homework, probably around 90% of the time, there will be no partition numbers where the derivative fails to exist. It will occur some of the time, but the majority of the time, your partition numbers will specifically come from wherever this thing is equal to 0. So this is a polynomial. It's defined everywhere. So there's nowhere that the original function is not differentiable. Therefore, I'm just going to start by setting this equal to 0 and solving it. Okay, to deal with this equality or equation here, I can factor a 3 out, which leaves me with x squared minus 9 equals 0. And this is a difference of squares, which factors like this: x plus 3, x minus 3 equals 0. At this step, I want to use my zero product property from algebra to solve this equation. Remember, what that means is if I have a product of expressions that are equal to 0, then that implies that any one of these could have equaled 0. So 3 is not equal to 0. That's not doing anything for me out there. But if x plus 3 is equal to 0, then that implies that x could be equal to negative 3. And if x minus 3 is equal to 0, that implies that x would equal positive 3. So x is equal to plus or minus 3. These are the partition numbers. Now, what do we do with those? We create a number line. This is the thing that's going to be called the sign chart. And we put those numbers on the number line. So negative 3 and positive 3. Don't worry about scale. Don't worry about saying like, well, if negative 3 is here, then positive 3 should be closer or further away. That's not important. What's important is that you can see these 3 subintervals that the entire number line was cut up into. So what we're going to do now is determine what is happening to f prime on each of these subintervals. Sorry, my printer's making a bunch of noise. And basically, remember, the goal is to determine if the original function is increasing or decreasing. But the original function is only increasing if its derivative is positive, and it's only decreasing if its derivative is negative. And since we know what the derivative looks like, I can use any of these expressions that I have here. All I have to do is plug some number into that expression to determine if it comes out positive or negative. Now, the derivative can only be all positive or all negative on each subinterval. So what that means is I can just pick any test point that I want and plug it into the derivative, see if that comes out positive or negative. Whatever it comes out to, that's what's also happening over the entire subinterval. So for example, right here, if I were to pick x equals negative 10, okay? That's something that is to the left of negative 3 on this number line, so it belongs to this first subinterval here, the number negative 10. I could then go plug that into I could plug it into here, y prime is equal to 3x squared minus 27, or any factored version of that I want, to see if the result comes out positive or negative. To be clear, it doesn't matter what the actual number is that it comes out to. All that we care about is if it's positive or negative. Now, the reason I mention that is because I'm not going to actually evaluate the exact value that I get when I plug negative 10 in. I'm just going to ask myself, would this be positive or would it be negative? So plugging a negative 10 into this factored version of my derivative, 3 is a positive number, so it's always going to be positive. If I put a negative 10 in here, negative 10 plus 3 is negative 7, so I have a negative number there. Negative 10 minus 3 is negative 13, so I have a negative number there. By plugging in a negative 10 in for x, I have a positive times a negative times a negative, which would be positive. So on this subinterval, f prime is positive. Next, I pick a test value in this next subinterval from -3 to +3. 0 is the best choice. It's right in between there. And plugging 0 into things is generally easier than plugging anything else in. So if I plug a 0 into each of these three expressions, I'm going to have 3 times 3 times -3. That's a positive times a positive times a negative, which would be negative, less than 0. Finally, pick a number in this subinterval. This goes from 3 to infinity, so you can pick anything you want, maybe 100. It doesn't really matter. It just needs to be any number that's bigger than 3. Well, if I plug 100 into the x's in this expression here that I got from my derivative, I get positive times positive times positive. It's easy to verify that. So my derivative comes out positive. Okay? So now I have these three subintervals, and I can tell you which ones our function is increasing on and which one it's decreasing on. I'm noticing I used f prime here when we weren't originally calling this function f of x. So it's probably better. It would probably be better if I put y prime, but it doesn't really matter. You kind of get the same information. So I can say that y is increasing on this interval here, -infinity to -3. That's this subinterval. And also from 3 to infinity, y is decreasing on the only interval that we haven't talked about, -3 to +3. One thing I want to point out about this, these are all open intervals. I'm not using square brackets the way that we would if we were using closed intervals. And that's because at those endpoints of -3 and +3, the derivative is neither negative nor positive. It's equal to 0 at those values. That's how we got them in the first place. So the function is not decreasing or increasing at -3, but it is on the intervals that those partition numbers split our number line into. Let's try another example. Same idea, different function. So I have y equals x squared times the natural log of x. I want to determine whether it's increasing or where it's increasing or decreasing. First, determine the domain. Okay, so this is a product of two functions, a polynomial x squared, whose domain is all real numbers, and the natural log function, whose domain is all positive real numbers. That's the only place where I have a domain restriction. So the domain here is 0 to infinity. It's the positive real numbers. Okay. Now we want to find our partition numbers. So I find y prime. And this is going to require the product rule because I have a product of two functions. So remember, from the product rule, take the derivative of the first function, which is 2x, but leave the second function alone, natural log of x. Then leave the first function alone, but take the derivative of the second function. Derivative of natural log of x, so 1 over x. Notice that we get some cancellation here. So this is going to be equal to 2x times the natural log of x plus x. And remember, we're looking for where this thing fails to be differentiable, but the only place it would fail to be differentiable is where this is not defined, and that this is not defined for anything outside of this interval anyways. So we've already accounted for where this will not be differentiable in the domain itself. That means I really only care about where it's equal to 0. To solve this, this is a different equation. It involves an x and a natural log. Factor an x out. X times 2 ln of x plus 1. That is equal to 0. So I have a product of two things here. And if it's equal to 0, my zero product property says that either x is equal to 0 or 2 times the natural log of x plus 1 is equal to 0. So this leads to two possible solutions. Either x equals 0 or 2 times the natural log of x plus 1 is equal to 0. And this is something that we can solve. Subtract 1, divide by 2. I get the natural log of x is equal to negative 1/2, which I can solve for x by taking e to the power of both sides. That will cancel that natural log out so that x is equal to e to the negative 1/2 power. Okay? All right, two partition numbers, 0 and e to the negative 1/2 power. So I'm going to make my sign chart, but this time, because there is a domain restriction, I'm going to put the smaller of these two partition numbers all the way to the left, so 0. E to the negative 1/2 is positive because e to any power is positive. I'm going to put that there. And I have to remember that because the domain of my function only includes positive real numbers, there is nothing to the left of this 0 here that we're considering. In the previous example, I also had two partition numbers, but it gave me 3 subintervals to worry about. Here I only have 2 because the original function is not even defined in this subinterval over here. So I'm going to pick some values to plug into this. You have to choose something that's greater than 0, so positive, but less than e to the negative 1/2 power. One approach you could take is to use a calculator, plug e to the negative 1/2 power in to your function, and then see what do you get as a decimal, and then pick a smaller decimal that's still positive as my test point. However, I know that the exponential function e to the x is an increasing function. So what that means is that if I plug in a number that is smaller than this exponent for e to the x, so in other words, if I raise e to a smaller exponent, I will get a smaller value. So something that I know is smaller than negative 1/2 is negative 1. I can plug a negative 1 in. Okay, and actually I should not have written it that way. I should have written it, here, I'm going to redo my sign chart. I'm going to do it over here. Put 0 over here, e to the negative 1/2. To be consistent, I should have written it this way. Sorry about that. Okay, so let's think about what that would be, right? I'm plugging e to the negative 1 power into my derivative to determine if it comes out positive or negative. But my derivative I've given in several different forms because I simplified and factored things. So I'm going to come all the way up here and plug it in right here, okay? And I'm just going to talk through what happens. E to the negative 1, just like e to any power at all, it's a positive number. So here, when I plug an e to the negative 1 in for this x right there, it's positive. But what about on this side? Well, when I plug e to the negative 1 in for the x right here, the natural log of e to the negative 1 power, that natural log and the e cancel each other. That's the role of that logarithm. That would leave me with a negative 1 here. 2 times negative 1 is negative 2, plus 1 is negative 1, so I have a negative number in here. Positive times negative is negative. So my derivative would be negative. Now I want to pick a number that's larger than e to the negative 1/2. So e to the power of 0 would be larger, but e to the power of 0, just like anything to the power of 0, is really just the number 1. So I could use 1 as a test point over here. Plugging that in, if I were to plug 1 in for x here, that's 1, which is positive. The natural log of 1 is 0, so this becomes 2 times 0 plus 1, which is 1, also positive. Positive times positive gives me positive. So my derivative is positive on that subinterval. Okay, putting all of this together, I can say that y is increasing on which interval? So it was increasing on this second interval that we worked with, which is the interval from e to the negative 1/2 to infinity. And y is decreasing on this interval here, which goes from 0 to e to the negative 1/2. Okay, so that's going to be it for this video. We'll do some more with this concept starting in part 2.